Hello, everyone. Welcome back. It is a great pleasure to introduce our next speaker, Jacqueline Mesquita from Universidade de Brasilia and President of the Brazilian Mathematical Society, who will be talking about functional differential equations with state-dependent delays and overview and new trends. So, Professor, please start.
Okay, thank you very much for this introduction. At first, I would like to thank very much the invitation of Professor Duvan Cardona. It's a great pleasure to me to be here and to be able to talk about this talk. And also, I would like to apologize because I could not participate of the entire week. I know that we have a very intense week for this conference, but it coincides with the celebration of the birthday of the Brazilian Mathematical Society. So, and that's why I also had a very busy agenda this week. So I'm sorry for not being participating for all this conference, but I'm sure that it's a very high level conference. I saw the speakers, and usually Duvan Cardona, he organizes very great conference. So thank you very much for this invitation. And actually, I will talk about this more general type of a concept of periodicity in any time scale. So my co-authors are Professor Martin Bonner and Sabrina Streipert, both from the United States. Martin Bonner is from the Missouri University of Science and Technology, and Professor Sabrina Streipert is from the University of Pittsburgh. So we started this project in Oberwolfach in Germany. We spent some weeks there, and we decided to think how we could generalize the concept of periodicity. So we spent like 3 weeks, me and Sabrina, and in the past also we had some periods in a type of also Oberwolfach in Bedlewo in Poland. In Bedlewo, also in the Benek Center, we also started this conversation. So here it's me and Sabrina in Oberwolfach. So we start first explain a little what's the time scales calculus, because I'm not sure if everybody here is familiar with this type of concept. So it's a very recent theory. It started in 1988 with the defense of a PhD thesis of Stephen Hilger, and his main goal was to create a theory that could unify the discrete and continuous case. However, a time scale can unify much more than that, since a time scale is only a closed and no empty subset of the real numbers. So we can have a variety of examples for time scales. For example, we can have like a hybrid types of time scales. We can have like Cantor sets is a type of time scale, and we can have much more than that. So here, as I mentioned, time scales is only that definition. So we can have many different types of time scales, including one that's very important, that's called that's important for the quantum calculus and also for the quantum physics. And in order to be able to start to talk about this unification, we need some operators that are very important in order to be able to define our definition or concept of differentiability in time scales. Because if you see, we need that this concept unify the continuous case and also the discrete case and also the hybrid case, and these for any type of time scale. So we define the following operators that you can see here. So this one is the whole T, that's the background jump operator, that's some operator that goes back. And also we have the for-route jump operator that goes for route. So here is the infimo of the points in the time scales that define in the green function that's really important here, but in the identity. So we have here this operator. We have because of this definition and for the background jump operator, we have that it
Okay, I think Jacqueline has some problems of connection, right? Hello, Jacqueline.
I am very sorry. I called out. Yeah, sorry. My connection is not so good. So sorry. But okay, I will continue.
Please.
I will share my screen. I hope that I will not. Okay, I think I started here, yeah?
I think we were in the previous slide when we lost you.
Previous. Okay. Oh, sorry. Here?
Yes.
Yes, okay. So as I mentioned, so we're defining these gradient functions as the difference between the sigma of t and the identity. And since sigma of t is always bigger or equal t, so we have this gradient function is always bigger or equal 0. Then we define the concepts of these points depending on the for-route jump operator and the back-route jump operator. So we say that a point is right dense if our sigma t is equal t. And we say that it is right scattered if sigma t is bigger than t. And the left dense if we have a whole t equal t, and left scattered if the whole t is smaller than t. So it will depend on the operators in order to define our points. And here then we can define our concept of delta derivative. So here for that we need to define here this set that the time scales kappa that we say that here is given by these if we have the supremo of the time scales is finite, and we have that it coincides with our time scales when we have that the supremo is infinite. And then what we have here, we have a definition of a delta derivative of the function f at the point t. And here it's really important to see that it's really similar what we have for the continuous case, because usually in the continuous case, what we have is that our sigma t is equal to t. So this coincides what we have for the continuous case, but also it's really important for the discrete case because we also have that it coincides what we have in the difference operator for the discrete case. Well, so here we also define what is the isolated time scales, and for us, isolated time scales is the time scales that all points are right scattered or left scattered. So we have that they are both at the same time right scattered and left scattered. Also, we use this notation here that it means like we are composition of both functions. So here we have some properties concerning our derivatives. So this is a very important one that's we call it like a simple, useful formula because it's always satisfied. Also, we have the product rule concerning our derivatives, also the quotient rule. So here we have that. And if you see, it really coincides in the case of the continuous case, and the same happens with the discrete, but also we can have a much more examples depending on the time scales that we define. And here also it's really important to talk about this class of functions that are called regressive functions, because they are really important to define our exponential function in the sense of time scales. So here we say that a function is regressive if we have that this is different of 0 for all in the time scales. And the set of the regressive functions we denote by this one here. And then we have these two operations, so circle plus addition and the circle minus subtraction. So if you see, if we are in the real case, what we have is that this mu is equal 0 because sigma of t is equal t. So we have here that it's always satisfied. So all functions are regressive when we are in the continuous case. And more than that, so here the circle plus will be exactly the sum that we know, because this mu is equal 0 when we have the continuous case. And the same will happen here for the minus. The circle minus will be exactly the subtraction that we know. However, here we are very interested about other types of time scales, and it will make a lot of difference when you consider these types of time scales. And here is the definition of the exponential function. There are other ways to define an exponential function on time scales, but this is one that's really nice, that it's very similar what we have for the case continuous. Yeah, so we have that the unique solution of this problem is called for us the exponential function, and here it's denoted by this one here, and we assume that our p is a regressive function. So then we have a lot of properties concerning the exponential functions that you can see here, and this is really nice that we can use like a type of a semi-group properties. We also have some properties concerning the circle and also concerning the circle minus. So it's really okay. Also, we have a variation constant formula for the time scale. So they provide this expression here where we have this exponential function. So then now I will talk about the periodicity on isolated time scales. So in order to do that, we have this iterated shifts. So we define these iterated shifts that we say here, that will be the composition of this four-out jump operator omega times. So we have this one here. And also we will denote this one here, that's the composition, the same way as we made for F composition with sigma. And then what we have is that this one here is exactly this type of composition, but also we can compose first with a sigma and then with mu, or we can also do it the other way around. So this both here commute. Okay, so now using these iterated shifts, we can talk about some periodic function on isolated time scale. So here it's very important to mention that it was an open problem for many times, for a long time ago, because if you see, in order to have in the usual way, like the classical definition of periodic functions, we need to add such a type of additivity property concerning the time scales, because we don't know if we have like our t, and if we sum that with our period of the function, if we have that this now belongs to the time scales. So in order to define a periodic function on any time scales, usually we need to restrict that for the time scales that have the additivity property. But it was too restricted if we see, because we cannot consider many types of time scales in that sense. So because of that, we decided that we needed on isolated time scales, for example, because we'd like to encompass all isolated time scales. So here is the definition that then we realized that it could encompass all types of isolated timescales. So here we say that a function is omega periodic if we have that this equality here is satisfied. So the set of all omega periodic functions is denoted by this here, and it satisfies this property. So we have that from that, also we have many types of properties. For example, we know that the N delta, only to remember that this mu is the sigma times composed with sigma omega times. And then we have this relation, and from this relation, we can also present this concept of omega periodicity in this way here. So we can say that a function is omega periodic if also this other property here is satisfied. And then when we see the results concerning certain types of time scales, we can see that it coincides what we really have for many different types of time scales. For example, here, this one is the quantum scale. And if we use our definition of periodic functions, we can see that it coincides what we have in our specific case here for this quantum calculus. So in the past, Bonner and Chioshon, they introduced the omega periodicity for quantum calculus, and we can see that it really coincides when we have this case for our definition. Also for these other time scales, we can see that it also coincides here, and the same for the integers number set, that we can see that again, we can have the same definition that we usually have for this one here. Okay, so, but this one, as I mentioned before, it's like for the isolated time scales, because if you see, if we try to put this one for the any time scales, let's say for the continuous one, it will not work. And why that? Because if you see, we have that the P composed with nu. And nu here, as I mentioned, is the composition of the Forward jump operator omega times. And since in the continuous case, the sigma t is equal t, so even if you compose that omega times or much more than omega times, we will have that it will be the identity. So it won't have the trivial equality that P of t is equal P of t. So if we try to use this definition for the periodicity, we would have that all functions are omega periodic for the continuous case. So we needed something more general in order to define that for the continuous case. Then we realized some ideas that we could maybe change a little this definition in order to encompass now all types of time scales. Then the idea that we had, so we first realized it for the continuous case, and then we put all them together for any time scales. So here we have that this new now is not that composition, but a differentiable and a strictly increasing function. So with this property now, we have that a function f is periodic with respect to nu if we have this equality here is satisfied. So here, it's really great because now we can have, for instance, that this nu of t is t plus omega, and in that case, we really have that these now coincides what we want for the continuous case. But here, if you see, we can have much more than that because our nu only needs to be some differentiable and a strictly increasing function. Does not need to be, let's say, some different type of function. So here, for example, if you, as I mentioned before, if we have this nu of t equal t plus omega, so we have that this definition coincides what we have for the classical definition of periodicity. So that we have this equality here. But also that's really important to mention that usually when we think about periodic functions, somehow many studies restricted that for such a type of a continuity. But here, for example, we can have a much more general than that. We do not need to restrict that for continuous. So, for example, we could have that the Dirichlet function is also new periodic. Yeah, depending how you define your f. So here we have, just to mention, not as you define your f, but for example, 0 for one type, if you have a t belongs to the rational, and 1 if it does not belongs. And then since the sum of two rational is a rational, so if omega is a rational, so then we have, in this case, that's a new periodic function. Okay, so here also in this example, we have that our constant function is omega periodic, but in that case, we need to have that our nu is given by this, or that our t is equal 0. So in both cases, we have that is a new periodics, but in that specific type of nu, otherwise we do not have. So also here from this more general definition, we have that our function is not periodic. This one here, we have that is not periodic, okay, in the classical sense. But in our specific case, from this more general type of function, we have that this one here is omega periodic in this sense when we have this nu here. So that's nice because we can expand the types of functions that are periodic and it's not periodic in the classical sense. And here, the one thing that's really nice is because we preserve the property concerning the integration of the periodic functions, so that we have in the classical sense. So I will also comment here this. So here also we have that in the case of the trigonometric function like cosine and sine, we will only have this is omega periodic if we have this nu given by this one here. But that's okay because this is really consistent what we have for the classical definition of periodicity. So here just to mention, so if we define this capital F nu as this integral here, as I mentioned, what we have is exactly the property concerning our integral. So if we see first, what we have from this lemma is that if our F nu is defined by that expression here, that integrating from t to the nu of t of this small f here. So what we have is exactly that if our f is nu periodic, this will be equal 0, which means that this function here is constant, yes, this f of nu, because the derivative is 0, but this means that this is constant. So it's really nice because in the intervals that we have this type of size, let's say, we have that it's constant when we have that f is a new periodic function. And this is the property that we can see that is satisfied in the classical case. So that's why we are really interested about this type of property. So just a small proof of this relation here that we have. So if we define our h of t equal this integral here from t0 to t, what we see is that our f nu that comes is the integral that comes from t to nu of t will be exactly this h of a nu of t minus h of t. Then we can use the chain rule. We can derive it here and use the chain rule for this first part here. And then it appears this term here, then we have a this equality. And then what's happening here is that the derivative here from the definition is exactly this small f nu t. So here we have that, but this is exactly what we want. So here we have this lemma is proven. Then now we have that from that, we have this theorem that is also true because as we mentioned, we know that the constant, so it does not depend on our t. So we can also have that one. So because of the previous lemma, this f nu, the derivative is equal that, but if f is nu periodic, then this is equal 0, which means that this F nu is constant. That exactly does not depend on t. So if I change t and t0, I have that this equality here. So here, just another example for that case in order to see. So as I mentioned before, in our case, our f of t is nu periodic if we consider our nu given by this logarithmic function. And now we need to see if it works in that case, okay? So because it's a different case, so it would be nice to see if this property will work here. And yeah, it will work from our theorem, because if you see, we have that this will be equal that by the definition of our nu t. And then if we have here, if we do some integration here, we have this exactly will be our what we have, and then cancel these two, and then we have omega. But this is the same to have this equality here, okay? Because again, you can cancel, and then you can have this omega. Then what we have is that this is exactly this integral here, and then this is our nu of f. So we have this equality here, and then we have that. Here also we have other types of properties concerning our periodic functions, and that's again very important, a type of property concerning the integral. That it's really important to prove our results, because usually we are very interested to investigate it like a periodicity for differential equations, and then we need to integrate. So it's really important to keep those properties in that case. So here again, if we have that our function f is nu periodic, then we have this equality here. So if we have this difference here, if I integrate it, it's the same. That's to do that for our nu. So this is what we understand from the periodicity or the type of property. It would be the same if we have, for example, our nu as the special case, like nu of t is equal to t plus omega. It will be the same one as we have for the classical case. In the case that this integral here is exactly equal a plus omega and until b plus omega. And then, since I have that f is nu periodic here, so we have that this integral here from the nu periodicity will be equal that one here. And here again, using this, here first, sorry, we are using the substitution like a change of variables. So we have this equality. And then now using the nu periodicity of function f, we have this other equality. So we have this equality here. So also another property that we also have for the n periodic function that also is preserved here is that if we have a function that's omega periodic, so we know that it's also 2 omega periodic. So here, for example, we have that this p mu is included here in that composition. So if it's nu periodic, it's also nu composed with nu periodic. So we assume that f is nu periodic, and then we show that, yeah, exactly, our function will be nu composed with nu periodic. So here we call it this nu tilde as this composition here. And then if we use the definition here of this nu tilde, we have this exactly is the definition. And then using the fact that our function is nu periodic, we have that. And again, applying the fact that f is nu periodic, we have that one. So exactly, we have that our f is nu composed with nu periodic. Also here, what we have is that given two nu periodic functions, we have the linear combination of these two linear nu periodic function is also nu periodic function. So, and in order to see that, so we again applied this thing here, and then using the distribution, we have that, and using the fact that f is nu periodic, we know that this is equal f of t, and then knowing that our g is nu periodic, we have that this is equal g of t. And then we have exactly what we want. So we have that this is a new periodic. And okay, so here again, just to emphasize that we are not using the continuity in any part. So all those properties that we had before, they remain true for this continuous function. So it only needs to satisfy the property to be a new periodic. And also here we have another property that brings that the product of two new periodic functions is not necessarily new periodic function. And here is some examples. If I have, for example, alpha is a new periodic function, and if our G satisfies this equality here, then we have that the multiplication f of G will be new periodic here. But if you see our G is not new periodic, if I put new periodic, I will have not this, the product will be new periodic. It could not be true in that case. So here are something that direction that we worked very hard to bring this definition. And the nice thing is that now we can work in periodic functions in the periodicity concept in a more like a unified way. Like for all time scales that we can have. For example, continuous cases, discrete cases, hybrid cases, quantum calculus. So we do not need like to study the quantum calculus in a different way, like not looking to the other types of time scales, because it was what we had in the past. So we worked with the time scales that had the additivity properties, and then we studied them, and then we studied in a separate way other types of time scales that we do not have this additivity property. For example, the case of quantum scales, that is very important for quantum calculus and in quantum physics. But here now, with this unified definition, we can have like this unified way, so we can work with all time scales in just one way, just one. Like we have this definition is applied for all types of time scales. So here now we have many future projects, like we now are investigating about averaging principle for time scales in this unified way. And in the case, of course, the periodic averaging principle, that we have some equation, and that the solution of this nonlinear equation can be approached by the solution of some linear equation that autonomous equation usually, that we can arrive using the averaging principle. So using this fact about the periodicity. So we are working that. Also, we are working in some basic properties concerning periodicity, like some population models, some directions with this. So working here with Professor Martin Borner and Professor Sabrina Streipert. So that's it. Thank you very much for your attention.
Okay, thank you, Professor Mesquita, for your really nice talk. So is there any question? You can raise your hand and then you can unmute yourself if you wish. Okay, I have a very broad question. I hope it is well posed. If I may, are there any extension to more dimensions? So instead of working with sets in R, are there any results working with sets in R2 or Rn or something like that?
Yeah, actually, you mean like using this definition or using other types of definition?
Yeah, so for example, your definition of timescales that you already said that they were non-empty closed sets. So doing that, for example, in Rn, and then
Yeah.
you're working,
Yeah,
finding everything the same way.
Yeah. Actually, there is one book from Professor Martin Bonner and Guzenov that they work exactly with that. They work with. They have this book that work with RN, and also the good thing is that when you have, for example, more than one coordinate, you can considering different types of time scales for each coordinate. So it's really nice. And there are several works in that direction, like partial differential equations on time scales. Also, we have many contributions in that direction, especially, for example, for numerical simulations, because you can also recover the behavior of your solution for the continuous cases. So it's really great. Yeah, we have many things in that direction, but it's something that it needs to be explored more. It was explored, but not as much as the potential that it has. So there are many open questions yet in that directions, but we have this very important contribution from Professor Martin Bonner and Guzenov that they have this very interesting book for RN and also for the time scales in N dimension.
Okay. Yes, Duan, go ahead.
Okay, Professor Jacqueline Mesquita, thank you very much for your very nice presentation. So I have the following question. I know that maybe you are very interested in more or less in the Euclidean setting because you have very specific probably applications in mind, right? But my question goes maybe beyond in the abstract setting. Because how much of the, let's say, Euclidean group structure you are using in the definition of this class of new periodicity, right? Maybe, do you think it's possible to make extensions to another kind of groups?
I think so. I think it's possible. Actually, there are some studies, including the time scales using other types of topology. There are also such a type of convergences that people use, like a felt topology or the type. And I think it's really possible, but we only explore it like in the usual sense, let's say, using, as you mentioned, like the Euclidean ones and also the topology that comes from the real number set. So, but it's also possible to extend for more general types of topology and also other types of distance also.
Thank you very much.
You're welcome.
Okay, thank you. Is there any other question or any other follow-up question? Okay, so if there is no more questions, so let me thank you again, Professor Mesquita, for your talk. And I think
very much.
Okay, and we end here. Okay, thank you, everyone. So the one you can finish.
Okay. Okay, thank you very much, Aaron. Then, if Professor Jacqueline Mesquita agree, then maybe we can continue with the closing ceremony.
Yeah, sure.
Then, okay, let me share the screen. Just we are going to have a very brief program for this closing. first starting with some words of Professor Jacqueline Mesquita, who actually is currently the president of the Brazilian Mathematical Society. Later, I myself will provide some words. Probably I will invite maybe some people in the audience who want to share some words also in an informal way. But then, I pass the word to Professor Mesquita then to continue.
Thank you very much, Duvan. I appreciate a lot the invitation. It's a great honor to me to be here in this closing. And I would like to say that this community from mathematicians from Latin America is really important for the Brazilian Mathematical Society, and we are like accomplishing all these movements that Duvan is doing for the mathematics from Latin America, and I think it's really, really important. So this event, for example, I could see that it was a very high scientific program. So I thank a lot Professor Duvan Cardona for organizing this conference of this very high level conference. So I think it's really important for the mathematics from Latin America and to consolidate more this relationship between mathematicians from around of the world and also from Latin America. I think we have a very good mathematics that are doing here. And I think Professor Duvan Cardona with this conference can show that the importance of the mathematics that's produced here in Latin America. So thank you very much for this opportunity and also to say some words. But I would like to say that on behalf of the Brazilian Mathematical Society, that you can count with our support on those initiatives. And it's our great pleasure to collaborate with these types of events. So, and also with all those initiatives that you are doing for Latin America. For example, we are now editing a book for women in Latin America, and Professor Duvan Cardona also had supported us a lot with these initiatives. So I would like to really thank you very much for that. Because I think we really need to consolidate and to strengthen the relation between the mathematicians from Latin America and think in the way how we can improve the mathematics in Latin America, because we have very good mathematicians, but sometimes we do not have the financial sources to do mathematics or to invite some important researchers to come and also to do some travel to have this internationalization. But I know that we have a very important mathematicians and very solid and with a lot of talent here in Latin America. So I think those initiatives for the Latin America mathematicians and also to consolidate the mathematics here are really important. So I would like to thank for the organizers on behalf of Professor Duvan Cardona for these initiatives, and say that the Brazilian Mathematical Society is here for collaborating with them. And thank you very much, and congratulations once more for this very beautiful conference.
Okay, thank you very much, Professor Jacqueline Mesquita. So just let me continue then. Let me say to all of you, to all the participants, thank you very much for taking part of this conference. As you know, we have celebrated here the mathematical life of Professor Luigi Rodino. I think maybe in a way in which mathematicians can enjoy, right? With mathematics of the highest level, and also giving the opportunity to mathematicians from underrepresented communities to present their work. After the words of Professor Jacqueline Mesquita, in her role, I mentioned before, of leading woman mathematician as president of the Brazilian Mathematical Society, and after the words of Professor Uwe Keller, the president of ISAAC, that he shared with us during the opening ceremony, I just can say thanks to the organizers. You can see here the photos of the young organizers of this conference. So Ias Castro from the Universidad del Atlántico, Santiago Correa, who before was in the Universidad de Antioquia, but now currently is in Augsburg University in Germany. Richard de la Cruz from Universidad Pedagógica y Tecnológica de Colombia, and Alex Picuamaya, who always was helping us with the technical support. Also, I would like to extend my thanks to my gratitude to Julian from EduMedios and to Alexandra from EduMedios also, who were also helping us with the streaming of the conference in YouTube. To Alexandra Garcia and Aaron Ramirez, who also were helping us in presenting several sessions. And just to close my speech, I would like to thanks to all the participants, and hopefully see all of you the next year with more ICMAN activities. So thank you very much. So thank you. Now I stop sharing the screen. I don't know if some participant want to say something, and if someone wants to share some words, and if not, Aaron, okay, Aaron, please go ahead.
Hello. Can I say it in Spanish or is it?
As you prefer. If
Okay.
you prefer to do in English, it's okay.
Yeah.
Also.
Okay, it is more an advertisement more than anything. So I belong to a national society, medical society. So they asked me if I can share with you some event that we will be hosting next week. So I just wanted to ask if it is okay that I post that in the chat. Yes. So just send the link. Okay. Thank you. So that's it. Thank you.
Right. Just maybe let me say that Aaron Ramirez and Carlos Canjura, both of them are members of the Association of Mathematicians from El Salvador. Carlos Canjura is the president of that society, and both of them are part of our agreement between Latin American societies and Central American societies with ICMAN to organize joint conference with mathematicians from El Salvador. And then Aaron Ramirez is one of the organizers of one colloquium that El Salvador is organizing for the next week. So if someone wants to, let's say, see what the mathematicians from El Salvador are doing these days, maybe then you can visit the website that already Aaron shared with us in the chat. So I really recommend to all of you to visit the website of this conference. And thank you to Aaron for reminding me this also. Okay, so thank you very much. Thank you very much to all of you, to Professor Luigi Rodino, Professor Owe Keller for joining us, and to all of you. So Jair, you want to say something?
Yes. Thank you very much, Duvan. Thanks all colleagues from Brazil, from Colombia, from. I would like to give an information. There is a Math Morocco list, email. It's more than 4,000 email list address. So if you want to spread some information, you can send it to me, and then I can spread in all the word. Okay.
Okay. Thank you very much.
Yes. I already done these things for this conference, and I want also to say that there was during this COVID period an experience with the African Seminar of Mathematics. So I may put you in contact with those colleagues in Africa, And then we may think about connecting Africa and Latin America and also people from India and Asia, so that we can think about some seminary once during a month with 2 or 3 talks, so that we can meet again in a regular form. So you can think about the form you see convenient, so
Right.
that we can connect all these people in one kind of seminary, that all these continents can contact, can be present, and also people from Europe and all the countries. But this initiative is very nice. So there was similar in Africa, and then we may make this connection, and thinks that the people that are very dynamic and enthusiastic and make connection between them, so that we can think about to meet once in a month, like a kind of this big seminary, but with 3 talks or not too much, so that people can wait for this day, and then we meet again, and then we put some questions or talk about new directions or perspective, or what are the hot subjects, what is going on, so that can people that follow can say, okay, maybe they can work on that direction or something like that. So just
Sure.
a suggestion.
Sure, that's a very nice idea. Let's
Yes, and
keep
thank
in
you very
contact.
much for
Let's
this
keep in touch.
initiative, and for this act, for this conference. Very nice. Thank you very much, Duval.
Thank you very much. Okay. Nino, Professor Mangiavitse, yes, please.
My gratitude to organizers for such interesting and nice conference. Thank you so much. So till we meet again.
Sure. Okay, thank you very much. So, let's officially
I
close the
wonder,
conference.
sorry, do you plan to send certificates of
Yes.
participating?
Yes, the certificates for the speakers. Even Santiago Correa is preparing all these files.
Okay, thank you so much.
You will receive one email from him soon.
Okay, thank you so much. So,
Okay, thank you. Okay, let's close the conference officially. Thank you very much to all of you. See you in another ICMAN conference. Bye-bye. Bye-bye.